Hello.
Hey, hi, Amit.
Hi, hi.
Hi.
Hi, Ratna.
How are you? How was the previous week?
Oh, it
Yeah,
was
it's
a
okay.
little busy.
Okay. Yeah. Yeah. I mean, like hope you're able to go through the second and third chapter, right?
Second and third. Huh,
I mean,
like
like
PCA.
PCA part.
Huh.
Yeah.
The third chapter,
Okay.
I was not able to go through it fully. Uh, but
Okay.
whatever I was able to go through, uh, I'll be presenting the like
Yeah.
next half. I'll be presenting next time. I hope that's fine.
Yeah. So like whatever we can do today, we'll try to do it. Like if we get over with PCA,
Yeah,
then we can proceed with the probability.
right.
Yeah, I mean, some parts of probability are, I think, just basic parts probably everyone is familiar with. I'm not sure, but since like everyone said that they are familiar with introductory parts in mathematics, so
Yeah,
uh,
anyway, I'll be touching upon everything just
sure,
to,
sure, sure.
yeah.
I was looking for additional resources to make this book like complete in some
True.
sense, but yeah, so there are some video lectures, but still I did not find much exercises which like everyone can solve. to-
Yeah, even I was actually the reason I couldn't go through the full book is that because as I was going through topics, I was looking to like clarify my understanding and then proceed. If it was just to read what is there, it's fairly straightforward. It's all equations. And okay, this is the equation of this distribution, that distribution. It's more like a reference manual, but I was just
Yeah,
referring to a few things and trying to understand. So I was like, okay, till here, I'm good. After this,
yeah.
need to look into this
Yeah,
more.
Yeah, so I think what we can do, I also have the same observation, not just for probability, but for everything. So,
Correct.
all right, so what we can do is, I have lots of problems. I just went through a few of the lecture videos, and I have some access to a few of the resources. So there are a lot of problems, and I myself, I mentioned earlier as well. When I solve problem, I realize that I have not learned anything, right? When you solve the
Exactly.
problem, right? So what we can do is whatever, and not just for this session but going forward as well, uh, we can go over whatever the concepts that we have covered, what have been covered in the book, because
Hmm.
these are like summary kind of a thing. We can go to as deep as we can, and then in the following week, we can solve problems. I can upload the problems beforehand so that everybody can solve, including myself, and then we can discuss that, right? So it would be good. But without problem solving, especially for linear algebra and probability, everything is just a philosophy. Everybody knows about all these definitions. I mean, there is nothing new
Right,
that.
that's true. And most of the time, what is important is okay, thinking of it in terms of probability and
Right,
like thinking of a problem in terms of okay, you can solve it with probabilities. That intuition is what we need.
right,
Because this is, it's just if you need to remember something, you can come back to this book and think of, okay, what was covariance? I don't remember that big,
right,
long, like formula, and I can come back to that. But yeah, as you said, right? It's more like, I mean, even if what I noticed was, even if we read all of this, after we read, you just forget. But if you try solving something with it, I think you'll remember how to work with it.
right,
So that's what I realized, that this book is not for maybe I felt like book is more for someone to refresh like the math concept, like not even concepts, but the math formulae. At least the first, like linear algebra and probability, when I read, it felt like it's just a refresher of the formulae. You can keep it like a cheat sheet. I didn't feel like it
Yeah.
was trying to build any intuition towards anything. So I did not actually like it.
Yeah.
Yeah, yeah. I mean, like I also felt that, but like whenever I try to read this book, what I'm trying to do is I'm trying to understand why the author has only included like this part and
Huh.
not the other parts in this book. So why is this part so important for the authors? So I'm thinking in that manner,
Right.
but still this book is not complete. And if we, as Suman said, that if we solve more exercises or some problems on it, we can brainstorm in a more methodical manner, I guess.
Right. Also, I remember taking that mathematics for machine learning specialization on Coursera a while back. I felt like that had actually covered all of the basics, and they were actually teaching with examples, not like giving formulae or not mathematically, but more like if any concept that they had, they started off with an example saying, assume, even probability, they started off with an example saying, okay, what if a kid is selected at random, what is the chance that the kid plays soccer? How would you think of it? And that's how it starts, and then it defines, okay, probability is this. So it's more example based. I felt like that probability and statistics by that it's by deep learning.ai itself. I felt that was full of examples, and it had like labs also to code and everything. So that was good. And from there, you can actually go deeper into advanced topics.
Okay. So I think we can do one thing, like we can uh, get intuition from several resources, and we can, for like summarizing everything, we can use this book also. That also we can do, like
Mm,
as we go ahead. For a particular topic, if you want to explore in depth what else is there outside,
right.
you can explore everything and then come back to this book again.
Mm,
Okay, great. So I think we are only four today, or some people can join later on. We can start perhaps with CA.
Okay. So, yeah, shall I share my screen?
Yeah, yes, please go ahead.
Okay. Just 1 second. Okay, just let me know if you are able to see my screen. Okay, let me share.
Yes, yes.
Can you see my screen? Okay, perfect. Okay, all right. So what just like how everybody just mentioned, so it was a little difficult for me to understand the book in the first place. So what I tried to do was I tried to went through a few of the other books and then try to build some intuition, and then I just noted down the important aspects of that. So there are different approaches that I've realized that in PCA that generally people talk about. Everything drives to the same conclusion, but there are different perspectives to look at. Just like Sujit sir, I think last week he also mentioned intuition behind that, reducing the dimension. But from mathematical standpoint, how that looks like and why this works, right? So after this, in the book, it just showcase the summary of that, basically the formula and then the derivation of that. Okay, so one of the book that I read was data driven. I'll share this a book, the beautiful book. I just this is not from an computer science, purely computer science background, but Nathan is from mostly from mathematics and engineering background, so fluid dynamics and all that. So the intuition that he built was, I felt it's pretty good. So I'll try to explain that, and then there is other literature I read. I'll explain that in a while. So PCA is basically, it's one of the application of SVD, we can think of it, and there are different names of that, like proper mode decomposition, imperial orthogonal function, and so on and so forth. So these are the different terms coined by different researchers and scientists over last 100 years or so. It's quite an old algorithm, I think in 1930s or something like, but it's very old. So let's say we take an example of a spring, right? Just like this is just to build an intuition, okay? And then we will try to solve this. So let's say you have a mass, some object, and there is a spring. And what we have to do is we just need to find when we put what is that function f. We know that f equal to mass into acceleration, and acceleration is second derivative of the position, like velocities. So we know this formula is nothing new in that. And I've put everything here because I don't have that access to share my iPad from my laptop. So that's why every text is here. But basically, we know that this force is mass into acceleration, and we can define this function. And if you go to physics, the force of the spring is nothing but m, second derivative of mass into second derivative of force, and it would be equal to negative of w square f, which is in the opposite direction, right? So these forces are similar. So we are not interested in that maths, but basic intuition is, let's say we are completely blindfolded and we have to solve this problem by just data, right? So we just have data, and what kind of data we have? Assume that camera was invented before we came up with this formula, force equal to mass into acceleration. Let's say we had no idea about this formula, but we had access to cameras. So camera was invented before, let's say, let's assume that. So in that case, we will put, let's say, 3 cameras, right? And then what we will do is we will take images. We will take images from different angles. In this case, we just have 3 cameras, but in real world, it would be like, let's say, hundreds of cameras, doesn't matter. Now we will just now imagine that we don't know what this is, but we are just having, we can just close our eyes and we can imagine that we just got 3 images from 3 cameras, and we have no idea what these images are and all this, but we have to come up with that hypothesis. Now in that case, let's say this camera 1, 2, and 3. This is the coordinates, because every image that it will take, it will have some x and y, and this x and y will be very much different from camera 1 to camera 3 and camera 2, because you are taking an image from one angle, I am taking an image from another angle, my position of the camera is different, your position of camera is different. So everybody's xy is different, but everyone is sharing 2 numbers, which is representation of the activity that is happening at any point in time, right? So let's say now it's 10 a.m. Sujit, you, me, everyone have taken an image, and we just added in an array. So this is my data point, XA, YA, XB, YB, XC, YC, right? So these are the 3 data points. I just stacked it in a column vector. So in this point, now this is one data point at one timestamp. Of course, we need to have multiple data across multiple timestamp, but let's stay with one data point. And in this data point, there could be 2 things that will happen, which is very natural. One is noise. People may not take images in the right way. They will tilt the camera and all that. So not every point will have exact data. My second image might be my kid was calling me and I just tilted my hand by accident or something like that. So not all data points would be correct, but noise we have to take care. Let's assume that we have all the camera persons have stable hand and they are very focused in taking images, right? Now, noise, if we can handle somehow, redundancy is something that we have to understand, because if you look at this, we know that all these three images is not needed, right? Because this object is just moving in one direction. It's basically 1 degree of freedom, right? It's just it's just going up and down in the z-axis. So we know that only one data point is good enough, right? So like you just tell me the vertical up and down, that's all. That would be good enough. But how do we know this? We don't know that. So this is where we have to come up with some redundancy technique. At this point, we have 6 dimensional data, but how can we know that which direction to just look for? And we are done. Otherwise, these are all redundant. So the idea is how do we measure the independence of this data, like how these data points are independent to each other. So that is the whole task. So this is where the intuition of reducing the dimension, or in the signal processing, like compressing the signal and send it across to the other place. These are the intuition that scientists and researchers were thinking about, right? How we can compress the data without reducing much of the information. Of course, when we are reducing, there will be some loss, but how much loss? I mean, there is some amount of loss we can accept. Now, before we solve this, by the way, till this point, is it okay? I kind of very much monologue. So in case you have anything, you can stop me.
Nothing from me.
Okay.
It's great. Yeah.
Okay. Okay. So now, before we will come back to this problem, but let's say, let's try to revise this variance and covariance, and this is part of probability as well. So let's say we have 2 data point. Okay, this is in n dimension, A1, A2, A3, AN, B1, B2, B3, Bn, like the n dimension. If I want to know the variance of A, like how much A varies, I can simply do A transpose, and 1 by n minus 1 is just a scaling factor. We can ignore it for now. But this tells us what is the variance in A, and the B tells us what is the variance in B, right? So for one example would be like, let's say A is salary of a person, right? So how much salary that everybody gets, right? So that would be like from 1,000 rupees to, let's say, 1 crore rupees, right? It's a huge variance. So bigger the number is, the variance is bigger. Smaller the number, the variance is smaller. Let's say vector B is, let's say, attitude of a person. So I have a big attitude. Everybody is having big attitude. So maybe B transpose may not be of that of significant difference when I look at everybody's characteristics in terms of this, because let's say attitude is high for everyone. So how do I know whether it's Suman or Ambani? It's only when we go and see, okay, Suman's salary is this much, Ambani's salary is this much. We know that, okay, this is what is more important than this. So basically, this is the variance. And this we can see in this 3 couple of curve sine waves. If you see, green is less capturing less variance because it doesn't change, although the mean is 0. Okay, so that's the assumption we have to make. And the red is like it's swinging with a greater amplitude, and blue is even further. Now, this is only about within a particular variable. How do we know whether how much A and B are dependent or independent, right? And this is where covariance comes in. So it's exactly same, but now in place of doing this within A and B and so on and so forth, we will do one with another, like how A is related to B. So it's A dot B transpose. It's just a dot product. It basically tells how much vector A is going towards vector B, or how close is vector A with respect to vector B. So if they are in the same direction, it's like the value would be very high. But if they are not going in the same direction, the value is 0, right? So that's how we can think about it. So if A and B are going in the same direction, it would be 1. That's the maximum. And here we are assuming the length of the vector is 1, right? So that's the assumption that we are making, although this will hold true even if the vector is not of length 1, but let's assume this, and this assumption we will use it later on. So these are the two extreme cases. If two vectors are in the same direction, it will be 1. The two vectors are orthogonal. Like let's say this x-axis is my thought process, the y-axis is my wife's thought process. It's completely independent, right? So I want to stay home, she wants to go out, something like that. But let's say the first one, when we got married, whatever she says, I used to say that. So there was a lot of similarity between both of us. So basically, with variance and covariance, we can understand two things: how two data points are related to each other, that is covariance, and second one is how much the variability within a particular data point. So that is the variance. So with that in mind, now let's come back to our problem. And here we don't have one data point, we have many data points. So in this case, we have to come up with something which captures for the whole data point. So that's why we have covariance metrics. It's just a higher dimension. And the way that we can do it is, previously it was within a vector, now it's within a matrix. So here, again, you can ignore the scaling part. It's not of that importance now. So now if you see here, I will just reduce the size so that I can capture this data point, but just keep this data point in mind. There are 6 points. Now, if we do this covariance matrix and X transpose, we get something like this. Okay? So the first column, and this is the one column, and this is the one row. And if you keep on multiplying, we will see that the diagonal elements would be the variance, and the off-diagonal elements would be covariance. Right? So it's like how, let's say, x1, xa, that is this one, right? xa with xa, then the second element would be xa, ya, right? And so on and so forth. So all these are covariance, and the diagonal elements will be the variance. Now, if you think about this, we have now reduced our space to a 6 by 6. So here we are talking about 6 because it's a 6-dimensional data. But imagine there are thousands of camera, then there will be 1,000 by 1,000. Doesn't matter how much data we have, this is the matrix that we will end up in. Now, if you think about this, the off-diagonal element actually tells us how dependent or independent are those data points, right? So if you just like in previously, we understood that if this number, like covariance, are very high, right, that means they are very much dependent, right? But if they are very small, right, that means they are quite independent. So what we essentially want is, we want to make all these off-diagonal elements, just get rid of this, because those all are duplicate data or redundant data, not duplicate, redundant data. That is what our objective is. So if we somehow find out if we somehow get rid of this off-diagonal elements, then it would be great, right? Because if those are very big numbers, we don't care. So what we will end up with is just the diagonal elements. And if they are small, we know that those are not that important thing. But if they are large, we know that there are a lot of things happening, right? So there is a lot of variability, just like salary of a person, right? So there is a lot of variability. So what we are interested to do is, we got the CX. This is the matrix that we got, right? This is the CX matrix. We somehow, if we can make it to diagonal, then that's good enough. So that would be a good frame of reference for us, where there is no redundancy or there is no duplicacy of information. So all we want is somehow come up with something where we can make all this off diagonal 0. That means there is no redundancy in the data. So now if we come back to our problem, we knew that our data matrix was X. Now what we can do is we can do X transpose, and we know that that would be S, this lambda S inverse, where this S is the matrix of eigenvalues of X transpose. And from where we are getting this? We are getting this from our data, right? How we have constructed this CX. Now what we can do is, now this X was the data that we had. Now we wanted to come up with a diagonal matrix. So that is where our objective is. Our objective is to come up with this diagonal matrix somehow. How we have to do it, that is what is the task now. But we have to come to that point. So now what we can do is, we know this is a very general, this is from eigenvalue decomposition or eigen decomposition we have learned last week as well, that this is where it stands, right? X transpose equal to S lambda S inverse or S transpose, whatever, because it's an symmetric matrix, it would be same. So now let's say if we now convert this X, because that was the raw data that we had, and multiply with S transpose. So what we are essentially doing a transformation of our data, right? So we are transforming the data into a new basis, basically. It's nothing fancy here. And why we are doing it? We want to make that metric a diagonal metric. That's a whole objective. So this is the new frame of reference for us. And if we now calculate the variance of this, covariance of this matrix Y, we will again do it like similar way as previously. Y transpose, we replace Y with X transpose X. And if we just open this bracket, we will see X transpose X, X transpose S. And now if we just replace this X transpose, which we have identified here, right? This is a given fact. We will realize that S transpose S is 1 because we consider that it's a unit length. So everything will be 1 and we will end up with just lambda. So now if you see, we got one matrix with only diagonal elements, nothing, there is no noise here. And we will figure out, I mean, we will see that this is just in one direction. And that is what the problem was, right? If you have a camera with multiple angles, it's all redundant. We just need one degree of freedom where we can just see the object is moving up or down. Okay, so this is one of the approach. The another approach, what I've seen is, I mean, it's again the similar one where we have the data matrix, and using SVD, we know that X is, we can decompose any matrix into the form of this using SVD. Now we are just talking about SVD, U sigma V transpose. And what we can do is we just take the U vector matrix from here, and we transform X in a new space by multiplying it with U transpose. So basically, we take the data matrix, we decompose it using SVD, and after decomposing, we will get this U matrix. I'll just take that U matrix. I don't care about others, other matrix V. Okay, and now if we transform our X into a new space, U transpose X, and if we now find the covariance of this new matrix Y, covariance matrix, if we do the same way, Y transpose, and if we simplify this, you'll realize that we will end up with only sigma square, because U transpose U, V transpose V, U transpose U, all will be 1. And that is why we made that assumption that we should have a unit vector. And the reason that we want a unit vector is, I'll tell you in a while, in a more realistic fashion, so that we can concrete that intuition why we want a unit vector. Why can't we do it with any vector? So this will end up giving us sigma square. So from SVD, we are getting this. From eigenvalue, we got this. And we know for a fact that sigma square equal to lambda, right? I mean, that is something that we know from SVD as well. So basically, this is how we can transform our data in a space where we just focus on maximum variance. Okay. So before I conclude, there is one more perspective. I think this is from a more we started off with a mechanical thing and came up to this point, but now this is more from a machine learning standpoint, right? So let's say we have all these data points, right? All these different data points, and there are two features, only two. Now forget about that camera thing. Okay, this is more from a machine learning standpoint. Let's say we have just two features, and we know that from looking at this data point, we know that this two features is not needed. If I somehow come up with this line, red line, and project all this point in this red line, right? And if you can visualize this red line as a vertical line, we can represent this whole data using just one-dimensional data, right? But again, there will be some noise, because if you see, if I project all this, I will be considering this residuals, right? These are the errors. If I just project everything on this line, which is okay. That's why when we do PCA or dimensional reduction, we say that there will be some information loss, but we can live with that. Now, if you look at this formulation of our setup, we don't know this line. That is what our objective is, to find this line. And we have to find a line which maximizes this variance of data. I can always create a line like this, right, in the horizontal way, but it will not capture all the variance. So if we now try to derive this, right, we can think of it like this. All we are interested in is just this direction. We don't care about this length of this vector, right, which is this red vector. Even if I take this blue vector, which is just a unit length, assume that this is a unit length, I am interested to know only that direction where the variability is high. Okay, so that's why we generally consider U to be a unit vector, because I can play with this unit vector only, right? We don't have to go to a specific vector, right? And I'll tell you one more reasoning which the professor gave. It's a fantastic illustration. I'll just share in a minute. So let's try to prove this. So this proof it's more mathematical, where assume that you don't know eigenvalue or anything. We will derive, that eigen in SVD, that sigmas are the maximum, the biggest sigma or biggest lambda contains the biggest variance. We will derive that. So let's say I'll just increase the font. Yeah. So let's some notation. If you see that x with a bar below, it's a vector. If only x, it's a scalar, and it's a capital X, it's a matrix. Okay. So let's try to derive PCA now. So assume that you have this point, right? And these are the x point, and every point is a vector of d dimension. Okay. So imagine that in the camera example, we just consider x1, which was a column vector. And now we have x2, x3, x4 to xn. So this is the d by n matrix. Okay. And every point is in RD. And the objective is, if I somehow convert this data into, let's say, some other space R, let's say RP, and P is less than D, I'm good with that, right? So that is what my objective is. So all I have to do, I want is from this illustration is I have to come up with this U vector, right? That is the objective. And after coming with this U vector, we have to project all the points on that. So if I project this X point in that U1 vector, I don't know yet what is that U1 vector. We have not discovered this U1 vector, but let's say we have this, we denote this vector as U1. After we get this vector, we have to project that. So we can do the projection on this, like U1 transpose X. And then our objective is the variance of this U1 transpose X is as large as possible, right? So this is basically an optimization problem, right? So we have to find a U1 such that the variance is maximum, okay? Now, how we can do that? So this is our objective function, where the variance, we have to find U1 such that the variance is maximum. And this is a very difficult problem to solve, right? And let's say, let's see how we can solve this. Okay, so what is the variance of U1 transpose X, right? What is the variance? So we have to first find the variance, and then we have to try to maximize that. But how can we do that? So if this is on the right hand side, this is just for one data point. I think the professor explained that. So if I have a one-dimensional data point, like 1D data, and whose mean is mu and sigma, or variance is, let's say, sigma, and we multiply each data by C, the mu changes by C mu, and the variance changes by C square. It's quadratic, right? It just it changes like that. Similarly, if I now consider this new point, or in this case, this is not a 1D data, so this is a D-dimensional data, and assume that S is the covariance matrix. What would be the variance of this? Because here we are just doing a transformation, right? It's just X, U1 transpose X. So the variance of this, like the variance of U1 transpose X, would be nothing but U1 transpose S U1. So we have to now maximize this, right? These are just the dimension. If you see, U1 is 1 by D, this is D by D, and U1 is again D by 1. And if you do this multiplication, you'll get a scalar. Now the point is, we have to maximize that. What is the maximum? How can I maximize this variance? Now, there is a quadratic function. If you multiply this, and it will come up with something like this, and there won't be any upper bound, because if you give me a u and you can tell me that, okay, Suman, this is the u which maximizes the variance, what I can do is I can just multiply u with 2u, right? So that will again be another second maximum, right? So there is no end to this maximization problem. So how we can solve this? So this is where we will add one constraint, where we will say that you have to find the maximum of this with a constraint that U transpose is 1, or basically it's a unitary matrix, right? So this is again the constraint optimization problem. But how we can remove this constraint? We can use something called Lagrangian. And so this is what in the book also they have mentioned. So when we convert any optimization problem from a constraint space to a non-constraint space, we can use Lagrangian. So just ignore this formula for a bit. The way that Lagrangian, we can think of it, let's say you have a function fx, and these are like red circles, and we are given a constraint of gxy, right? And we have to find the right fxy, which is maximum, right? So if you see, this is also a fxy function, this is also an fxy function, but the largest red circle is the one we are looking for. And this is where the slope of gxy and fxy are same, right? So this is the saddle point, what Lagrangian finds out, right, by the derivation. And if we think about Lagrangian, it is fx minus lambda gx. I'm not telling this y thing, like fxy minus lambda into gxy minus c. And if I take the derivative of this, because the slope would be same at this point, we will end up with this. So this is basically Lagrangian, right? So derivative of fxy is equal to lambda times derivative of gxy. So similarly, in this case, in our case as well, we have to maximize this with this constraint. So we will do the same thing here. We will do lambda u1 transpose u1 minus 1. And now I have to find the u1. The objective is to find the u1. Just like here, we have done the derivative. Here also, we will do the derivative. So we will we take the derivative of this function L with respect to u1. Now, if you think about this, what this is doing, this u1 is a d by 1 vector, right? And this whole thing, this whole expression is just a number. We will get a 1 by d, d by d, d by 1. It's just a number. So essentially, we are finding a derivative of a number or a scalar with respect to a vector. That means how much a vector will change such that the number changes. So if I change the vector by a certain point, how much that number or that scalar changes, right? So that is what this derivative is. And if we do that derivative, we will find, so we are essentially doing the derivative of this. It's U transpose SU and minus lambda U transpose U. And if you do the derivative, we will see this 2SU1, because the derivative of this L derivative of U1, since U1 is a vector and this L is a scalar, we will end up in a vector, right? It's just that how much it changes. So the derivative is 2SU1. If we just, and even if intuitively you think of it as SU square, it's 2SU, right? Intuitively also it makes sense. And here as well, similarly, you will get 2 lambda 1 U1. And if we solve this, you will get SU1 lambda U1. So we have not even touched about eigenvalue and anything, but we came up with something like this. And this sounds very, or this looks very similar, right? Where we are transforming a vector by multiplying with a matrix, and we are getting the same vector, but a scaled one. And there is nothing but our eigenvalue. This is U1 is eigenvector and lambda 1 is the eigenvalue. But the question is, we have to find, like now we at least we got to a place where we can find U1 and lambda 1, right? So that's very, very much easy now, because S is coming from data matrix, and U1 and lambda 1 we can easily find out. It's just an eigenvalue and eigenvector we have to find out, right, of this matrix. Now, one thing you can, let me see if I have it written here. Okay, so one thing you can consider is, or rather, if you think about it, why we think that this lambda, because here it is saying just lambda 1, right? So, and if S is a D by D matrix, we know we will get D lambdas, right? Maximum we can get D lambdas, right? If a matrix is 3 by 3, we can get maximum 3 different eigenvalues. But how do we know, or how we say that the maximum eigenvalue or the eigenvector correspond to the biggest eigenvalue will have the maximum variance? Why that hypothesis came? I mean, why we say that? If you think about it, our objective function was this, right? We have to maximize this U1 transpose SU1. And if you now replace S with this, right? SU1 is lambda U1. And if you just replace this part, this SU1, right, with lambda U1, and lambda is a constant, you take it in left-hand side, you will see U1 transpose U1. And this is a unit vector. We started with that assumption. That will be 1. And then you will end up that maximizing this is nothing but this lambda. So bigger the lambda, the maximum that variance is. So that's why we say that the maximum, the first principal component is the vector which corresponds to the largest lambda. So similarly, second lambda would be the second principal component, and so on. So it's just the same derivation from different perspectives. This one is doing an optimization using Lagrangian without having an intuition or understanding of SVD and anything like that. Only thing that we have to induce our understanding of eigenvalue is when we see this equation SU1 lambda U1, where we only know the only known element here is just S, because that is coming from our data set. U1 and lambda 1 is something that we can come up with using this eigenvalue equation, right? So that's how we can think of PCM. Yeah, so it's the same thing that this one is explained in the book as well. But yeah, so that's what I had. So Again, sorry about the monologue, but does this make sense? Or if you want to correct anything or add something?
So in the last part, sorry, you have to accept that the Lagrangian is a valid, that equation is a valid equation, right?
Yeah, this one.
The value of L, if you go further up, I think.
Okay, yeah.
There, this one.
Right.
Yeah.
Yes, so this is coming from Lagrangian. So this is because we want Lagrangian. We don't care about Lagrangian. We care about this. But this is a optimization problem with a constraint, and it's very difficult, by the nature of optimization. So that's why we try to convert this maximization problem to an unconstrained optimization problem. And the way that we can convert and constraint to an unconstrained optimization problem is by using Lagrangian. So this is what I've noted on the right hand side is just what Lagrangian is at a very high level. So that's how we can derive, because ultimately all we want is to find out this U1 vectors. That's the whole thing.
I had some doubts.
Yeah.
So why are we maximizing the variance?
Yeah. Yeah. That's a good question. So let me just go back. Yeah, I actually forgot to mention that. Yeah. So if you see this here in this data point, right? So if you look at this data point, there are two axes, X and Y, and every data point is a two-dimensional data. But if you see, if I have to give you this data, I have to give you 1, 2, 3, 4, 5, 6. 6 into every data point is two-dimensional. That is 6 into 12 numbers. I have to give it to you, Amit, to convey this information, what is there in this chart. But I feel that if I somehow can reduce the dimension, and how we can do that, I will try to see that whatever data point I have, how I can give you a smaller set of data point, but conveying the same information. Okay, so that's how I want to come up with a vector. Okay, with a vector, and then project all these data points into this vector, and I just give you that number, because once I project all these green points into this red line or this blue vector, all data point is nothing but just one point, right? One number, because once I project, it will be a straight line. You can think of it as a straight line with 1, 2, 3, 4, 5, 6 points. So I will just give you now 6 points rather than giving you 12 points before to convey the same information. Now there are different different 6 numbers, different set of 6 numbers I can give you. And I want to give you the projection or the numbers which contains the information that this data at present contain. And that is possible only when I pick the right vector which has the maximum which captures the maximum variance of this data set. Because if you see, if I draw this red line is like this, if there is another line like this, right? If it is where my mouse pointer is, you see the variance is very less, right? Variance is just here to here. Variance is very, very less. So if I project in this line, this point, and this point, and this point, all this point will squeezed into one point, right? In this line. So I can give you the same 6 numbers, but that will be very, very similar, right? Those 6 numbers would look something like this. Let's say 1, 1.1, 1.2, 1.11, like this. But in this case, if I give you the 6 numbers, it will be having the maximum variance, right? So it will be, let's say 1, let's say this is 2, this is 2.5, this is 3, 4, and so on. So basically the idea is we have to project the data into a new space where we capture the maximum variance. And there are 2 ways to do that. One, what we have seen by maximizing the variance. The other way to look at it is, if you just calculate the distance from here, right, from this point to this red line, and this point to this red line, if you somehow minimize the distance between this point and the line, so we can think of that maximization of variance problem to a minimization of this distance problem. It's both the same, because ultimately both the optimization problem, if we come up with a vector, those vector will be same. So in a lot of books and literature, you will find that for PCA, the vector which maximizes the variance is the same vector which minimizes the sum of the distance of these points to this line.
Yeah. Yeah, got it. Yeah, I think it makes sense. Yes.
Okay. So there is
I had one more.
Yeah, tell me.
Yeah, I had one more doubt. I think in the later part, much down. Yeah, so actually, what I was thinking is U transpose and SU is like it's getting S is kind of becoming kind of constant, and it's kind of, this is generally U transpose U is kind of dot product. So is
Yes.
it?
So for S,
And
S is S would be if you have the data and if you give me the data points, right? So let's say you have captured all the data from all sensor cameras and all that. Once you give me the data, this S matrix is a frozen fact, right? So doesn't change. S is just the covariance matrix of the data set. What changes is this U vector. So intuitively, if you think about it, these points are frozen points, right? Now, what I do with this point, it's up to me, right? I multiply each point with something else, that's up to me. So that's how I come up with that matrix S. Now, what is variable here is this red line. I might find this red line, or there would be another line like this, and like that. So how I know this red line? So that red line is what we are interested to find. And we have to find a red line such that the variance of this is maximum. That variance of those points on that vector, that's a projection, right? A U transpose X, that's a projection of those points into this new space. And that new space is defined by that vector. And whatever is the variance of that, I want to maximize that. So that is the intention. Give me one U vector which maximizes the variance of my data set.
yeah, and as a result, we got like X equals to lambda U, right?
Yeah, right. Yeah.
So that means it is very much aligned with U. Like, so for example, whenever like I was visualizing U transpose U or U transpose X as dot product of U and X, although they are not like vectors, they are matrices.
Oh, okay.
And we are getting X as lambda U, which means that it is very much in the direction of U.
Okay, got it. Right.
So, but then I was wondering, why is the covariance, I mean, why is the variance maximizing at that point if it is
Okay.
aligned with U?
Okay.
Is there any intuition?
Yeah. So, okay, let me think about it. So here, what we are doing is we are, if you think about it, in this space, right, at this point, right, this S we have derived from the data which captures the information. This S matrix is the most important matrix here. It captures the information of how one point is related to another data point, and also within within a point there are different features, right? Here we have D features, right? What is the variance of those D features? All this information is captured into this matrix S, right? So this is the matrix S that we have. Now, when we are doing this, right? So when we are so let me just go back here. When we come to this S, right? We started with the data X. Now we don't like that data. So just like in this example, I've told you is that I can always give this 6 data points to you in 12 numbers, right? But I'm not interested in giving you that. But I'm interested to give you smaller number of points, but still preserving this information, what these 6 numbers are representing. So somehow I have to change those 12 numbers by doing some linear transformation, right? And that what linear transformation I will do? I have to multiply with some matrix, and what matrix I can give. And that matrix is the covariance matrix. And if you look at this covariance matrix, by the definition of covariance matrix, how it looks like, where the diagonal elements are the variance, and the off-diagonal elements are the covariance. Right? So when you see this, and when you multiply this with your vector, right? So or the projection, then you will ultimately get the maximum variance when you ultimately find that. I got your question, but I think if you take because I also had the same thing. If you take a small 2x2 data set, and if you compute this metrics and then do that, it will be very easy. So what I will do is I will share you this PDF. This is a beautiful PDF. It's a 140 pages, but it's just an animation, okay? But it actually tells you everything, like what the example I've taken, right? It creates that covariance matrix, and then it will tell you what is the relationship between each variable and across different variables. And when you multiply it, right, when you actually do the multiplication, why it is giving you that maximum variance. So, that you can intuitively figure out.
Yeah, yes, sure. One more like intuition just now I got is that basically U transpose X we can treat is like if U is set of vectors,
Yeah.
means columns if you represent it as vectors or even eigenvectors, then U transpose X, if the variance is maximized, we are kind of getting the maximum in every for every point of for every feature of U.
Correct. So if you think about it here, right? If you think about it, right? So consider all these green points. Projection of this green point into this it will come here. The projection of this will come here, right? And if you now take all these points, the variance is maximum. If you take a red line here, the variance will be maximum. Or if you take the red line here and do the projection, all this projection will, the range of that projections, right? It won't be that maximum, but this one would be the maximum. And in case there is an error, right? Because when I'm just putting this point back to this point, I'm actually losing some information because I'm just, getting rid of this residual.
Yeah. Yes.
So this residue argument, is that the the intuition behind say the first diagonal element being greater than the second, being greater than the third, and so on?
Correct.
Okay,
That's
right.
correct.
Okay.
So in fact, that's the last point I actually forgot to mention is that a lot of time in machine learning, we will get this information from the field that compress the data such that I preserve 90% of the information. That means I can afford to lose only 10% of information. So in that case, what we will do is we will first take the principal components. So if that's a d-dimensional data, I will have d principal components, maximum d principal components. And what I will do is I will create the first U1 by calculating the lambda 1, and then I will see what is the variance I'm getting, because one thing I have not covered here, and in the book also they have not mentioned, but you can go back to your data from this projection as well, right? So what people will do is they will find out the variance that is captured by lambda 1, If it is not capturing 90%, I will go to the second principal component and I will see that, okay, if I now add lambda1 and lambda2, is it coming to 90%? If not, I'll go to lambda3. So let's say in lambda3, if I add lambda1, lambda2, lambda3, it is giving us, let's say 95%. Then I know that, okay, I have to send this 3 vectors, or basically the projection in this 3 vector space. And that's how we define that in principal component analysis, how many principal components I should have, in my for my problem, whether it's only 1 component, 2 component, or 3. It depends on how much variability I want to preserve in my data set.
Okay. And like, where is the dimension reduction happening here?
Where, Amit?
Where is the dimension reduction happening here?
Oh,
Like,
okay. Dimension reduction. Okay. Yeah. So if you think about it, so here we have U1 and U2, right? If I have just U1 and U2, my X data point, right? So my X data point will convert into a 2-dimensional point, right? 2D data. Whereas my data point was, let's say, in 100 dimension. So it's just like we are moving from R100 to R2 space by doing a matrix multiplication. And that matrix is nothing but the covariance matrix.
Yeah, basically you zeroize any non-principal components. Say you're capturing, say, 90%, and that's the first 3, right? And your S matrix is like maybe 100. So you just take the first 3, every other diagonal element becomes 0. So when you multiply, so anything beyond that, so essentially it becomes like U and V becomes like long, skinny matrices effectively because of the zeros. So you still end up getting an m by n matrix that you started off with, but with a lot of the the principal component or the lesser principal components or the non-principal components removed. Sorry. Yeah.
Yeah. So let me just try to. So let's say U1 and we got U2, right? And this is 1 by this would be I'm considering column vector. So D column and D by 1, and similarly this will be also D by 1, right? And my data point, I'm just considering 1 data point, right? So 1 data point could be like 1000, let's say 100 dimension, right? So now I have to project in this U1, U2. So my matrix will be U1, U2. Okay? And I have to multiply this X data point, and what I will get is a 2 cross 1 matrix, or 2 cross 1, or a vector in 2D. Because what I will essentially do is I will put this U1 in the first column of this matrix and U2 in the second column of the matrix, and I will just multiply with my data data X, and this is D cross 1, or rather here I'm considering D as let's say 100, so I can consider this was let's see, yeah. So you can consider D as anything, right? So D can be 100. So if D is 100, then U1 will be also 100 cross 1, 100 cross 1. But this matrix, right? This one would be 100 cross 2. So we are going from R100 to R2, where R100 is coming from this. Right? This is the vector. I'm projecting it into this new space, and the resultant vector is 2 cross 1.
okay, so instead of like storing entire X vector, X matrix, like we will be storing 2 one-dimensional and D-dimensional vectors.
Yeah, so
So-
basically this resultant, this is actually there is no interpretation of that data, right? It's just a number. That's why we call it as a principal component. It's not if a data point having 100 features, let's say a name, sex, age, and all that, I will convert this into two-dimensional data, but that two-dimensional doesn't contain anything. Like it's intuitively, it's a mixture of all the features, right? And
Okay.
how those mixtures were built? Mixture was built based on the variance of different features in that data, right? But this is not a feature reduction. It's just I'm just considering the importance of all these features and coming up with a new representation of the data.
Okay. Okay.
So I uploaded this PDF in the Google Drive, and in fact I'll add some problems, but there are problems which I think Ratna was mentioning, right? So I'll add PCA problem, but there are a lot of problems on linear algebra. If anyone wants to look at it.
Sure.
Thanks. Yeah.
So, shall I share my screen?
Yeah.
Yeah, okay. Is my screen visible?
Yeah.
Okay. So today I'll be going over probability, but not the entire chapter. I'll be going over just the first part of it until the distribution. Those are like the like this basics, and then we have the common distributions and common functions and all that, right? I was thinking I'll cover that in the next session because it's not going to be done in this short duration. So the book starts by speaking about where probability is applicable in machine learning. So it says that there are two areas where probability is useful. One is trying to tell us how these systems reason. The other one is actually analyzing the behavior of machine learning systems, because machine learning heavily depends on using probability, because the outcomes are uncertain. And by knowing the probability, it will help us design these algorithms and make them work better if something is not working. And also by interpreting the outputs, we are able to make them adapt. So for an example, if we consider the spam detection algorithm, right? So here what it's doing is you have a machine learning model that takes an email and gives out the probability whether that email is spam or not. So here what it's doing is it's considering the probability whether it's spam or not based on the words within the email. This is kind of like applying Bayes' theorem, because we're calculating a probability given the words in the email. Spam detection is not an only example. We can think of other examples as well, like image recognition. We're trying to find the probability of cat giving the pixels of an image as the input, or like sentiment analysis. We are trying to understand the probability of the text being a happy sentiment or a sad sentiment given the words in the text, etc. So machine learning uses probability. And so what is probability? Probability is actually representing uncertainty and tries to give us rules or methods to make those uncertain statements. And there are two kinds of so there is certain and uncertain. By certain, we call it as deterministic variable, and uncertainty is also sometimes named as stochasticity. Stochasticity is usually when there is uncertainty that comes inherently in a system. That's when we say stochastic random uncertainty. So I just laid out the differences between them. So deterministic, you always have the same value. Stochasticity, there can be multiple values. Deterministic, it's always related to a fixed outcome. Stochasticity, you always those values that are the outcome of uncertain events based on an experiment that you conduct. Each time you get different values. An example that the book states is, say you have a CPU that executes each instruction flawlessly, and each time it gives you the same result, which is deterministic. But stochasticity can be something like, if you have a shipment, each time you get a shipment, the number of defective items in a shipment won't be the same. They'll be different. So that is a random number of things, right? And the book also talks about, makes a statement where it says sometimes it's more practical to use an uncertain rule rather than a simple uncertain rule rather than a complex certain one. And it gives an example saying that by just saying most birds fly, it is cheap to develop and it is useful broadly. But if you say something like most birds fly, but except for young ones that have still not learned how to fly, and some exception of birds like emu, which usually don't fly. And if you have a very complex descriptive statement or a rule, it is expensive to develop and most prone to failure, because most of the times it's not required to be very complex and certain. So that's where sometimes dealing with uncertainty is more practical, is what they state. Then, an example of deterministic could be a function which is like a quadratic function, like x square, where you know the value of x equals to 2. So that's another simple example that you can take. And then they talk about sources of uncertainty. So there is inherent stochasticity in the system being modeled, and they give an example of, say, in quantum mechanics, the dynamics of a subatomic particle is probabilistic in nature. Or if you have a hypothetical game of cards where if the cards are truly shuffled, then they'll be in random order. And another source of uncertainty is incomplete observability. What they mean by incomplete observability is sometimes all the variables that drive that particular behavior of the system are not observed. There is a term for this. Sometimes people call it confounding variables. So sometimes you don't observe those variables, and it's not possible to look at the system from a viewpoint of deterministic nature. And for this example, they give it as a Monty Hall problem. What Monty Hall problem is it is actually, I don't know if you guys have seen this on the television, where there is a game show where there are 3 doors and the contestant is asked to choose a door, and whatever is behind the door, they get that as a prize. And most of the times, only one door would be a car, and then the 2 other doors would be hiding a goat. So here, the author says that so the outcome from the contestant's viewpoint is uncertain, because out of the 3 doors, you don't know which door is hiding the car. But so once the contestant chooses one door, the outcomes become certain that the car must be in one of the either 2 doors. To be able to explain this a little more clearly, I actually have one second. I actually have a notebook where they actually explain it really well. 1 second. No, not this. Is there a way to hide this bar on top while sharing the screen? Oh yeah, okay, found it. Yeah. Am I audible?
Yes, yes.
Yeah,
Okay, sure. So yeah, I was talking about a course on Coursera by deeplearning.ai. They have a mathematics for ML specialization. So in one of the courses is about probability and statistics. So in one of their labs, they talk about this Monty Hall problem, and they try to show why it is so why the outcomes are no longer uncertain once the contestant has chosen a particular door. So here, I hope you guys understood the problem, so I won't be going into that. But into the solution. So once the contestant chooses a door, right, the host will actually ask if the contestant would want to change to another door or not, and later reveal a different door that is not the contestant's door. And we already know that so probability of each of the doors is equal, right? 1/3. But once the other door is revealed, we already know what that is. So the probability of the contestant's door having the car would become the complement, 1 minus 1/3, 2/3, because the other door didn't have a car. So now it is like this door has been revealed. So the probability that it exists in either of this is 2/3. So this is the conditional probability, right? So the probability of him winning, provided if he switched, would have been 2/3, because initially what he chose might not have the car. I will actually try to share this solution also, like share this notebook if possible, so that you can go through with this. But this is the problem where once the contestant chooses one door, it becomes certain what the outcome is going to be. So the next one is incomplete modeling. Incomplete modeling is when there is some information that is discarded, and that discarded information leads to uncertainty in the predictions. So here they give an example of the robot predicting. So a robot uses the location of the objects around itself, and then later discards that exact location information. So now the robot is not able to predict future location, because it's not exactly certain of the point where an object is. It can only give you an interval between like a range, because that precise information has been discarded. So these are the sources of uncertainty that they talk about. And the next one is, so they also go through the types of probability. One is the frequentist approach, and the other one is Bayesian. Frequentist approach is based on the frequencies of the event. Bayesian approach is based on the degree of belief or certainty, based on a perspective and probabilities from that perspective. So here its frequentist approach is the proportion of favorable outcomes of an event by total possible outcomes. Bayesian approach is based on the Bayes rule, which I'll talk about in the next few slides when it comes. An example of frequentist approach is to actually get a certain hand of cards in poker to win. And Bayesian approach is when a doctor tells you that a patient has, say, 40% chance of having flu. The same patient, if the patient goes for a second opinion and asks another doctor, the doctor might give a different percentage, might not be exactly the same. So that is a Bayesian approach where two different people assign different probabilities from their viewpoints, and this requires prior information to be also included. And they also talk about if you have enough common sense assumptions about the certainty, it is possible for the Bayesian probabilities to behave exactly as a frequentist probability as well. So it's possible for both of them to be the same, provided you have enough number of assumptions that you make. And then some rules of probability that I have here, which I guess everyone knows, but I'll just go through them. So this is the probability definition from a frequentist approach standpoint, which is number of outcomes of A. And here S is the sample space, so total number of possible outcomes, which is the sample space. And then you have the complement rule, which is what is the probability of the event not happening is 1 minus the event A. And then the product rule is when they're independent events, event A happening is not dependent, event B happening is not dependent on event A or vice versa, then it is, it can be treated as the product of the probabilities. And then we have the sum rule. By disjoint or mutually exclusive, what we mean is that their intersection is 0, so they are not basically they're independent and based on the product rule. Sorry, they're not. They're basically they're not. Their intersection is 0. That's what I'm referring to. So P of A union B will be P of A plus P of B, but joint events will have an intersection of both the events happening. And so this is again from that particular course itself, where I found a particular tool that is interactive, which would be able to show the probabilities. So say I choose a coin and toss it once. So the blue bar that it's showing is the observed probability in this experiment, and these are the theoretical probabilities. Since I flipped this coin only once, so the observed probability is heads in this particular experiment. Say I toss the coin 100 times. Then here we see that the observed probabilities are similar to the theoretical ones, because probabilities definition is also the same, right? Where what proportion of it happens, provided we repeat the experiment many number of times. So here we repeated the experiment 100 times, and heads is 0.5, tails is 0.5. Suppose we have a dice, we do the same for dice as well. So for a dice, the theoretical probability is 1/6, right? So we see that it's similar to the theoretical probability, provided we roll the dice 100 times. So this was an experiment for both of them. And then we go into random variables. So a random variable is a variable that can hold different values, and the author talks about it just being a description of states that are possible, and probability distribution is actually telling you what states the random variable can hold. So here again, there's a difference between discrete random variable and continuous random variable. Discrete random variable, basically they are discrete values and they are countable. Sometimes they can hold countable infinite number of values. So there can be many values which are countable. And continuous random variable, they're on an interval of infinite number of continuous values. And then we have examples for them. So an example for discrete random variable can be number of heads in a coin toss, or continuous random variable is time. Time is continuous. So if you're waiting for your bus, how much time does it take until it arrives? So can any of you tell me more examples of discrete or continuous random variables apart from these?
Could have dice throws, roulette wheels, right? So
Right.
discrete, yeah.
Right, correct.
Yeah, so I think continuous would be any outcome which cannot be which can be defined in a number line, basically, like which for example, let's say height of a person. What is the probability that the height of a person is let's say is less than 5 inches? We cannot say exactly 5 inches, or sorry, 5 feet, but what is the probability that the height of people is less than 5 feet?
Right. Correct. So yeah, there are many. So the a random variable can hold like it's just a variable that can hold different values, whether it is discrete or continuous. So that is what is stated here. Based on sorry, yeah, tell me.
Yeah, but the one small thing is on this continuous random variable. The point probability is 0, is it? Like
Yes.
intuitive, right? Okay.
Yeah. The point probability is 0.
Okay.
Because we can only look at probability within a range. At a point, it just becomes like a, so if you look at the, 1 second, let me just try to draw it. So for a continuous distribution, it's like a curve, right? And we take the area under the curve at a particular region, say A to B. So if you want, so the area under the curve from A to B would be this region. So we try to integrate line segments within that, and then the sum of all of it will be 0. So sorry, 1. This is for a region. But if you take a particular point here, it's just like a line segment, right? And then a line segment doesn't have
Yeah, the area is 0 basically.
area is 0.
Right.
Yeah, I
So
just wanted to add up there is a special function, I think it's mentioned, for which it is non-zero.
yeah, the Dirac function, right?
Yeah, the Dirac delta function is a kind of a limiting function where it is on a single point, but the area is non-zero because the value is infinity. It's like 0 into infinity kind of.
Correct.
Limit.
The Dirac function, yes, it is a single point, but it extends, like the height is infinity. So that one is, yes, the area is 1. That's right.
Oh, sure. Thanks. Yeah.
Okay.
Really helpful here.
Okay, I'll proceed then. Okay, so here we move on to the probability distributions. The probability distribution tells you how likely a random variable takes on each of the different states that it represents. And this the difference between these two is based on the random variable that it represents. So for a discrete random variable, it's a probability mass function, and for a continuous random variable, it's a probability density function. And for a probability mass function, it tells you the exact probability of each value of the random variable. for a density function, it's the rate at which you accumulate the probability around each point. I will actually try to draw the distributions after explaining this, but just showing you the differences. So probability mass function looks like this, where probability of the random variable taking a particular state x. Here it's an interval. So it's the x, which is the random variable, is between lower limit a and higher limit b. And that is the area under the probability distribution p. And we do the integral of p of x dx, which should be 1. Here, we also look at the different properties that a function must satisfy if it has to be a probability mass function. The probability should have all the possible states of the random variable. The probability should be between 0 and 1. And the sum of the probabilities should be 1. The same holds here. Here, we say that it should be greater than or equal to 0, but it need not be less than or equal to 1. It can extend beyond 1. And instead of sum, for probability mass function, we always take the sum because it's discrete. For probability density function, we take the integral.
So this is one thing I thought. I mean, maybe the integral kind of covers, the third condition covers the second condition and limits it to 1. Is that not correct? Does it actually go beyond 1, or is it implicitly bounded to 1 because of this integral?
I think so. The area is 1, but the distribution stretches beyond
Oh, I see. Okay,
the
okay,
limits,
I see. Okay,
right?
okay. Plus or minus infinity. Yeah.
Yeah,
Okay.
plus or minus infinity.
Right.
So we are
Okay.
talking about the area being 1, but here we are talking about the stretching beyond the limits.
Generally, the distribution is defined for only a and b. I mean, values between a and b. So apart from values beyond that, the probability distribution's value will be 0. So it won't contribute to the area, and overall area from minus infinity to infinity will be 1 in that case. One meaning that, like, the total chances that we have covered all the uncertainty.
Can you repeat that? Sorry, I didn't get it. Can you repeat that?
So I was just answering to the question that.
Okay.
Yeah. So the entire area between minus infinity and infinity is 1.
Right.
And yeah.
Okay.
No, but the px is the y-axis, right?
Yeah, px is the y-axis.
Yeah.
That is the distribution of probability. It's not the probability.
Oh, I see. Okay.
Yeah, distribution of probability.
Okay.
So how is where is the probability greater than in which part it is more and in which part?
And x-axis is the probability with minus 2 plus infinity. Okay, got it.
Oh yeah, correct. Okay. So to explain the differences and to understand the distribution simply, let's take an example. So suppose we are trying to flip 3 coins and we want to know, say, the random variable that we want to understand is what is the number of heads in the 3 coin tosses. I hope my handwriting is understandable. Let me know if you can't see it properly. So,
yeah, it's okay.
Okay, thanks. So now let's write down the outcomes. So this is coin 1, coin 2, coin 3. Let's say the first outcome is tails, tails, tails. Second outcome is tails, tails, heads, tails, heads. tails, heads, tails, tails, heads, 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 tails. I'm just numbering them. So these are our outcomes. So what we want is how many heads in 3 coin, number of heads in 3 coin tosses, right? So here we don't have any heads. These two have, sorry, one second. This is 0 heads. Both of these have 1 head. And then these two have 2 heads. This is 3 heads. So what we want,
The fourth one will come under 1 head.
yeah, right. The fourth one will come under 1 head, and I think I missed something here. Yeah, this is also 2 heads, right? Yeah.
Yes.
Yeah, right. So this is again 1 head. Okay. So what we want is we want to find x1 is equal to heads, and we take it as probability of x1 equals to 0 heads plus x1 equals to 1, x1 equals to 2 heads plus x1 equals to 3 heads. So because this is 8 outcomes, right? Denominator will be 8, and there's 1 outcome which has 0 heads, 3 outcomes which have 1 head, and 3 outcomes which have 2 heads, and 1 outcome which has 3 heads. And if you've noticed, 3 plus 6 plus, sorry, 1 head. 3 plus 3, 6, 7, 8. So it satisfies the, when you sum it up, it satisfies that the sum of the probabilities have to be 1. And if you try to plot this as a histogram, where x-axis is the number of heads, and 1 by 8 will be like this, 3 by 8, 3 by 8, 3 by 8. So this is how your probability mass function would look like. This is a simple example, but as you increase the number of coins, right, this probability mass function might become more like it might have many different levels and start looking like a normal distribution graph. So the way the probability distributes along these possible outcomes, they always seem to have a similar pattern. The same thing can be done for a PDF as well. So for a PDF, as Suman had asked, right, the exact value would be 0, probability of the exact value. We are talking of intervals in this case. So here it would be more like, this is the distribution. We calculate the probability over intervals. And for this, suppose if you're trying to find the probability that you will weight between, say, 1 to 2 minutes for your bus, or 2 to 3 minutes. So the probability in this case is calculated as between the range of 0 to 1 minute, which will be this bar, and then between the range of 1 to 2 minutes, which could be this bar, and so on. And then you take the area under the curve until whatever, say you want to calculate between this range. So you take the integral of this segment, say 0 to 5, and then you calculate the probability of x dx, which should give you 1. I mean, this is just to have a simple understanding of it. In the book, actually, they give uniform distribution as an example and try to make sense of how it satisfies all the criteria. So for a discrete random variable, uniform distribution, probability of that random variable taking different states is always 1 by k. If it is k states, it'll always be 1 by k. And if you add up all of these 1 by k's over I, it'll be 1. So it satisfies the summation rule. And for an interval of numbers, A and B, if they are the endpoints, then the uniform distribution is 1 by B minus A. Okay, so this is about the, this is about the distributions, and we can look at them in, so here's another tool which tries to see the different relationships between the distributions and running the experiments for it. So suppose we want to look at continuous uniform distribution. And then this is the parameters A and B. So here the uniform distribution is between A and B. Say we run it once, x is equal to 0.38. Say we run it 10 times. And then we run it 50 times. So it's still within that range. So the black line is, as you see, it's the PDF. And then if we want to see continuous normal distribution, we'll get to that when we get to normal distribution. But I just wanted to show the uniform distribution and run the experiment. And okay. So next we talk about joint and marginal distribution. Basically, joint distribution is when you have many variables at the same time. Joint distribution can be taken as P of x equal to x. X and y are the random variables, and the small x and capital, the smaller case value variables are the states. And if they are independent, they can be factorized as P of x times P of y. And marginal distribution is, say you want a subset of probability distribution over the subset of variables. Then you sum over the joint distribution for that subset, say y, or if you want it over x. This is for discrete, and this is for continuous. For this also, we can try looking at a problem. Okay, So yeah, let's say we have okay, age. Let's say we have ages of people and heights. So we have age as say 7, 7, 7, 8, 8. This is like a data set. And then we have heights as 45, 46. I'm not writing down the units or anything, but just take it as it is. And then 10 is. So let's try to put it as no limit. Age will be 7, 8, 9, 10. And then so age can be the X variable. And then heights can be the Y variable. So 45, 46, 47, 48, 49, 50. So here we're representing the probabilities. So 45, we have it occurring once, and then we have 10 samples, right? So we take it as 1 by 10. And then 46, we have two heights that are 46 for 7. So 2 by 10. And all of this is 0 for 7. For 8, we have 47, which is 2 by 10. The rest of it is 0. For 9, it is 49 and 3 by 10. 50 is 1 by 10. And then the rest of it is 0. For 10, we have just 50, 1 by 10. Rest of it is 0. So this is kind of like the joint distribution. And then for this, let's just represent it as a row itself. So for age, we'll say age is 8, 7, 8, 9, 10, right? What are the probabilities for age? For 7, it's 1 by 10. Sorry, probabilities for age, it's not 1 by 10, it's 3 by 10 because we are taking this row. So we add up, if you're considering for 7, we add up the probabilities. That's 3 by 10. For 8, it's 2 by 10. For 9, it's 4 by 10. And for 10 is 1 by 10. If we consider the same for heights, if we take 45, 46, 47, 48, 49, 50. Take the probabilities. Now we sum up over the columns, right? 1 by 10, 2 by 10, 3 by 10. 48 doesn't have anything, so it's 0. 49, 3 by 10, 1 by 10. So here, to find the marginal probability of say yeah, if we want to find the marginal probability of say 50, the age 50, what we do is we we keep the rows the same, right? We sum across all the rows X, and we want to find the probability of 50. So now that is 1 by 10 plus 1 by 10, 2 by 10. And if we want to do the same for age, what is the probability of 7? Which is, we already calculated it here, 3 by 10. So these are the marginal distribution. So here this is nothing but sum over the row, and here this is sum over the column. So if we look at if we look here, right, we've used if we look here, we've used the same formula. We tried to sum over the joint distribution. And we also calculated the joint distribution previously. So next is conditional probability and chain rule. So conditional probability is, it's again taking... Yeah, tell me.
Yeah, just one small thing. So here, basically in marginalization, what we are essentially doing is we keep one thing as fixed, and then we find the probability of the other distribution of the other one. Like here, X, given the age is 50, what could be what is the probability of the height, or I would say the other way around.
That's okay. But you're right. Given the height is 50,
correct,
what
right,
is
the
the
50.
probability of X? Right.
Got it. Yeah. Okay.
Sorry if I wasn't clear about that. But
No. You were very much clear. I just wanted to reiterate so that the understanding is correct. Yeah.
Okay. Any questions I forgot to ask in between, but if any of you have any questions, please interrupt me and ask me while I'm writing it down, so that doesn't sound confusing.
This was great. Yeah.
Okay. So then for conditional probability, it's like taking the probability of something given the condition of the value of another variable. So to give you an example of that, let's say, what is the probability of y equals, y is this, okay, let's see, y is heights, so I'm just writing it here. So y equals 49 given x equals to 9. Suppose we want to find this conditional probability. What we do is, so the conditional probabilities formula is this, right? It's the joint probability distribution by the probability of x equals to 9. I mean, we can see that from the definition. So it's x equal to x comma y equal to y by the probability of capital X equals to x. So that's what I've written down over here. And then we know that this is 3 by 10. X equals to 9 and x equals to 9 and y equals to 49, 3 by 10. This is what it is. And then probability of x equals to 9. So x equals to 9 is this, 4 by 10. So 3 by 10 is the conditional probability. So the probability of y equals to 49 given x equals to 9 is 3 by 4 from our distribution that we have here. And we also talk about the chain rule. So here with, So here, if we look at it, the chain rule of multiple random variables can be decomposed as the probability of the first random variable and the product of the conditional probabilities of the rest. So this is nothing but to simplify it, we want to say it's the probability of, sorry, let's take a simple example. A comma B comma C will be probability of A times the product of probability of B given C. I think this has been shown in the textbook also. So we can see that example in terms of like three variables and so on. I think, let me see.
This is not. I think you need one.
There is one more we have to add there, I guess.
Yes.
Yeah. So
Probability of C.
yeah, I don't remember, so that's why I was looking for that equation. 1 second. Yeah, conditional probability chain rule. So A.
Yeah, this is the one.
Oh yeah, this is the one. Sorry, my bad. But yeah, this is the one. So probability of A, B, C will be given by probability of A given B comma C times the probability of B, C. And what they try to do is they try to find what is the probability of B comma C. So that's B given C times BC. And then they try to substitute this into this equation, which will give you this
Yeah.
this chain of probabilities.
Yeah, just one small thing to add. So here, the way that I remember this is when I first looked at it. If you just look at the last equation, P A B C, it could be A B C D E F whatever. The way that I could get a head around this is we have here A B C. That means we want all these three events to occur at the same time. Right? So we can start with one of them. So let's say C. So first I have to find with, let's say, P of C. And then given C has already occurred. What is the probability of B? So that is the second element, B given C. And now B and C happened. Now I have to find the probability of A. And that's the first element. And that's how we can create the chain rule. And
right. So now that we know this, now that we know probabilities of B and C, because we already know that they've occurred, what is the probability of A given B and C? So this one. Right. Is that clear?
yeah.
Okay. I'll just move on.
Yes.
It's time. So do I go ahead or do I?
I think we can continue in the next session.
Okay.
I guess.
Yeah. Okay. I'll continue in the next session then. Stop sharing.
I had a question.
Yeah. Tell me.
So in like real life, we generally tend to round off the values, right? Like even if like there are real numbers, we tend to, for example, age can also be treated as a real number, but we always say as an integer. Or in general, everything we tend to round it to integers or to 2 decimal places everywhere. So technically, we should get discrete probability distributions everywhere. So then why are we studying about continuous distributions?
So technically, we actually discretize everything, even though we have continuous variables, right? Technically, when we are calculating something, we always approximate. If you've noticed, for everything, we try to take approximations. We can't like take the continuous distribution because you'll have to take into account the smallest of the decimal in precision, right?
Yes.
I think it's
Yes.
because we want to do calculus on it.
Huh.
Yeah.
That's also.
Yeah. And I think one of the things that it's when we talk about probabilities, always there is an error involved because we start off with itself with just a sample of data. We don't have the whole population data. And the second is in terms of discrete and continuous, there will be a lot of scenarios where we have to the data set itself is a continuous in nature. Like you mentioned, let's say height of a person. Here in this example, our scope of work or scope of data was just 5 district height. So that's a district variable for us. But in general, height is a continuous variable. So in that case, we have to find the probability of a continuous variable, and that's why we do integration, as Sujit sir also mentioned, and uh, and in fact there is an error, and that's why when we do when we differentiate, like when we integrate, there is a constant c that we keep, right, always. So that's kind of, you can intuitively think that integration, we can do a differentiation to get the number back, but we lose some information because that c differentiation of c is always 0. So whether it was 5 or 10 or 100, we don't know. So
Yeah.
there is always error involved in integration in a continuous variable. But there are scenarios where we have to deal with that. That's always there.
Okay. I did not get the C part. Like if you are dealing with like definite integrals,
No, no.
the
So
C won't be there, right?
yeah. So indefinite integrals, it won't be there. But when we create, when we in that context, when we do a integration, right, as we discussed initially, the whole distribution goes from minus infinity to plus infinity. Right? We scoped it to, let's say, a and b. So that's when we have that definite integral. But we actually scoped into within this, and within that distribution itself, there are infinite points which that integration covers. So that was just an intuition, but what I was
Okay.
trying to say is that in there will be situations where we have the random variable itself is continuous in nature. We cannot discretize that, and we cannot find, and that point probability also won't make any sense of those kind of data.
Yeah. So like I totally agree with the intuition about like if there is single point and infinite values, then the probability must be close to zero. And I think perhaps that also makes sense that we can use the continuous distributions to just assume the random variables in nature, so that even if we don't know how are they going to behave, the values the that we get in real life, we can just assume that they are going to behave in a continuous manner, so that we can predict them beforehand. Perhaps that would
Yeah.
make sense of uh, continuous distribution as well.
Yeah, right. I think in the later we will learn that there are, I mean, for continuous variable, when we find the distribution or any probability, there are different, depending on how the nature of the function is, there is always some assumption that we make. There is a lambda, there is a c, depending on different types of functions. So we start off solving the problem with an assumption that this is a certain type of distribution, right? Whether it's a logarithmic distribution or this distribution, normal distribution, and all that. So there is always an assumption to start off with, and it changes by that assumption, right? And that's why the parameters for all these continuous random variables, whether it's mu or sigma or lambda or exponential, like in exponential we have other constant. So those are the
Yeah, we
assumptions
have
that we
lambda.
start off with.
Yes. Awesome.
Also,
So yeah, yes.
so I was just going to say the comment about calculus, right? So because of that, it allows you to do simulations. So if you look at something like PyMC, right, where you basically model, or even probabilistic graphical models, where you model a situation using a set of distribution, to Suman's point. Like a hierarchy of distributions. It simplifies your calculations, and it also allows you to generate points or sample points from that fake distribution or the assumed distribution. So I think it simplifies calculations. That is the main reason for going continuous.
Yeah.
Yes. Great. So I really like today's presentations. I mean, they're great, and we can perhaps do the questions also, as you're suggesting. So how about like what to do in the next session? Should we also do questions regarding PC and probability?
Yeah, we could.
Yeah, we can. I'll share.
Or should we go for
yeah.
next chapter?
Yeah, I think
We are not done with the chapter.
we are not. Yeah, we are not done with the probability yet.
Yeah, I think it will take another hour, and then it will be done.
Yeah, right.
Okay, then we can, if we get time, we can do questions also next time.
Right.
Yeah, so what we can do is like maybe just to for the interest of time and everything, like this is just a thought. We can share the I can share and others can also share, and let's say for next 2 weeks, like next week as well as the following week, 14 days we can practice those problems, and in the session we can pick up 1 or 2 problem, and then we finish the probability by next class. And then in the following week after next, we can start with the chapter number 4. And during this time, we can brush up on the things that we have learned so far in linear algebra and probability, and solve problems and share in Slack maybe.
And that's actually a good idea. Like everyone, whoever comes up with problems that they find interesting, whether it's problems or
Anything, yeah.
like code samples or any snippets, anything, we share it. And then so maybe it can be like first half can be the session, and then the second half can be discussion on the problems. Say some of them are challenging or not understandable, and we can talk about it. Try to solve.
Sure. Yeah, that would be great. Yeah. Yeah, there was a few questions which were asked in one of the interview I was taking with one of my colleague. He was asking, even I also did not know. So those are good questions. So I can share those as well. I mean, anyone can, but yeah, that would be interesting.
Great.
So okay, so where like okay, so we'll store these problems in some Google Doc or something, so that it will be accessible every time. Anyone can go through it anytime.
Yeah.
Great.
Also, looking forward, I'll be out August 11th and 18th. So the week after next and the week after that. So I signed up for chapter 5 with the anticipation that chapter 4 will already happen during these 2 things, right? So just letting you guys know, there's like a gap in the spreadsheet. So yeah.
Okay. I can take chapter 4, I guess.
What is chapter 4?
That would be
there is like
computation.
Yeah, it talks about underflow, overflow, numeric stuff. Yeah.
Okay. Yeah.
Great. So I think chapter 4 will be on 10th probably. So chapter 5 will come on 17th, most probably.
Yeah. So in that case, I might even miss. So I'm out August 11 and 18, right? I'm not there. So, but if I'm guessing chapter 4 will take 2 days also, right? So I'm hoping at least, or the problem set will move forward. So in any case, so in that case, I'll take something further down. That's,
Yeah, and chapter 5 is, I think, really big. Chapter
Yeah.
5
it
is
is.
really big.
I personally feel by the time, I think the PC and probability, which I was just going through now, it will go away by next Saturday. So,
Oh, okay. Okay.
so Jit, even if you come after 2 months, you will, both our state would be same.
Yeah,
Okay.
we'll still be doing these again, I guess.
Okay. Yeah. So anyway, so just
Yeah, sure.
the reason I signed up for 5 is that's why I just wanted to mention.
Sure.
Okay.
Yeah.
Yeah, great. Cool, then we'll maintain one Google Doc for problems, and next time we'll discuss that along with chapter 3.
Yeah,
Cool.
sure.
Okay.
Okay.
Yeah.
Okay.
Thanks.
Thanks,
Thanks,
Vidit.
everyone.
Right. Thank you.
Thank you.
Thank
Bye.
you.
Bye.
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 Bye.